In this video, we will discuss aqueous solution reactions involving redox processes. As an example of a redox reaction, we have here the reaction between magnesium metal and elemental oxygen. The crucial thing is that we have oxidation numbers that are changing. In the case of the elemental magnesium, it has an oxidation number of 0. Likewise, the elemental oxygen, the atoms have oxidation numbers of 0. So all elements have oxidation numbers of 0. And after the reaction is completed, the magnesium has lost some electrons to produce magnesium ions, which are 2 plus in terms of oxidation number, and oxide ions, which are 2 minus. So in essence, the crucial thing in a redox reaction is that electrons are being transferred between the reactants to produce the products. And so we say that there are two different processes that occur. One of them is the oxidation, or one of the reactants is being oxidized by losing electrons. And in this case, this is magnesium. So magnesium goes to magnesium 2 plus along with 2 additional electrons, which are given up. And so in this case, the other species is being reduced. And this is where the oxidation number gets decreased. And we can think of this as a reaction in which an oxygen atom is gaining 2 electrons to form an oxide ion, which is 2 minus. So one way to be able to identify a redox reaction is to be able to look at the changes in the oxidation number and to be able to identify the half reactions in which electrons are either reactants or products. So an oxidation half reaction involves the loss of electrons. So in other words, electrons are a product of a half reaction that is an oxidation. And likewise, reduction is when we gain electrons, and so the electrons are a reactant in a half reaction. So as you see here for oxygen. As another example of a redox reaction, we see here the reaction between iron metal and copper 2 plus ions in aqueous solution. In this case, the products are iron 2 plus and copper, elemental copper. So in this case, we have assigned our oxidation numbers. So iron metal is in its elemental form, so it has a 0 oxidation number, whereas the copper 2 plus ion has a 2 plus oxidation number. The products, the iron 2 plus in aqueous solution has an oxidation number of 2 plus, and the copper is in its elemental form, so therefore is 0 in its oxidation number. So we can see that the iron is going to a higher positive oxidation number, so this must be as a result of losing negative charge, in this case the electrons, and by definition that is an oxidation. Whereas the reduction, the lowering of the oxidation number, is a process where the copper 2 plus ions are gaining 2 electrons to become copper metal. So, in terms of the half reactions, we can write the half reaction by writing the 2 species involved. In this case, we have an iron going to iron 2 plus. Now we have to worry about balancing charge, and we can balance, once we've balanced the elements involved, we can balance charge by adding electrons. We have to have both sides have the same amount of charge. So on the left side we have 0 overall charge, but on the right side we have 2 plus, and to get them to be the same, we have to add 2 negatives to the right hand side in the form of electrons. Likewise, we can write the oxidation half reaction in terms of copper. So the copper 2 plus is a reactant, whereas the copper metal is the product. Since we have the same number of copper atoms on both sides, now we can balance our charge by adding our 2 electrons to the left side of the reaction. So once we have balanced the total amount of elements on or atoms on both sides of the arrow and the charge on both sides of the arrow, we can then identify the species that are being oxidized and the species that are reduced. So at this stage we need to understand a little bit of vocabulary, and a term that is sometimes used is the idea of an oxidizing agent. In this case, an oxidizing agent is the species that facilitates the process of oxidation. And so in this case, the oxidizing agent is actually the species getting reduced. And so in this case, the species that acts as the oxidizing agent is the copper. And the copper 2 plus ion is accepting the electrons or facilitating the loss of the electrons from the iron, as you can see above. Now, the reducing agent, on the other hand, is the species that facilitates the reduction. And so in this particular case, then, the iron is the reducing agent. It is the thing that is giving up its electrons. In other words, it's the species that's getting oxidized. So you can always remember that if we're talking about an agent, it is the species that is doing the opposite process. Oxidizing agents get reduced, reducing agents get oxidized. So in order to do various quantitative calculations involving redox reactions, we can use these to do things like titrations. And so we need to know something about the overall balanced redox reaction. So as an example of a question, we have, what is the concentration of I3 minus in a 25 milliliter aqueous solution if 33.54 milliliters of a 0.108 molar potassium thiosulfate solution is required to completely react, causing the solution to change from a blue to a clear solution? You see here the balanced overall redox process. Notice that there are 3 iodine atoms on the left side of the arrow, and then there's a stoichiometric coefficient of 3 on the right in front of the I minus. Also then you can see that the thiosulfate, there's a stoichiometric coefficient of 2, giving 2 times 2 sulfurs, a total of 4 sulfurs on the left. And on the right hand side you also have 4 sulfurs. In addition, there are 6 oxygen atoms on the left, and you'll notice on the right there are also 6 oxygen atoms. The last thing to check and make sure this really is balanced is the total amount of charge on both sides. So the I3 minus is -1, whereas the S2O3 2 minus, there are 2 of those. So it's a total of 5 negatives on the left side of the arrow, whereas on the right there are 3 iodides, that's a total of 3 negatives, and then the S4O6 2 minus, so for a total of 5 minus on the right. Now, turning our attention to the question, we have a place to start in terms of, we have the number of milliliters and the concentration of the K2S2O3 solution. Note that this formula, K2S2O3, is corresponding to the potassium thiosulfate, which is one of the reactants. Thiosulfate is the reactant on the left-hand side of the arrow in our reaction. So what I would do is start with the volume of that solution, and so that is where we can start our problem. So the crucial thing to notice is that since the volume of the thiosulfate is given along with its molarity, we can determine the number of moles of that thiosulfate. Um, Remember that the potassium thiosulfate is a strong electrolyte, it's ionic compound. That's the source of the thiosulfate. And so in this particular case, then, the stoichiometry between K2S2O3 and the thiosulfate ion S2O32 minus is 1 to 1. So we convert that into liters and then use the molarity to determine the number of moles of the S2O3 minus or 3 2 minus ion. And then from the balanced chemical reaction, we can figure out how many moles of I3 minus are going to react with that. And the stoichiometry is 2 to 1. And then finally, that gives us the moles of I3 minus. At this point, to determine the molarity, we would take the number of moles and divide by the volume of the solution given in the question, which is the 25 milliliters. But of course, molarity is moles per liter, so we have to convert that into liters. Finally, we do the math, and we recognize that we need only, in this case, 3 significant digits because the molarity has 3 significant digits in it. And so we end up with our final answer of 7.24 times 10 to the negative 2 molar I3 minus.